will mosey in. So if we can start the recording, we can get going on this. Okay, the title of today's webinar is Accurate Quantitation of Low-Level Degradation Impurities for Biologics by Mass Spectral Accuracy. I think and I hope that you'll find this is a pretty interesting topic. It's an area that we've done a lot of very nice work in. And I'm your presenter. My name is Don Keel. I am the Marketing and Product Manager for Cerno, and Yongdong Wang, who's our CEO. This work was done in collaboration, and we'd like to give special thanks to Michael Petticord, who's at Bristol Myers Squibb in Brunswick, New Jersey. This is the outline of what we're going to be discussing today. The first part of the presentation, we're going to give you a little background on exactly how we perform this mass peak shape calibration to attain the spectral accuracy for doing accurate quantitation of unresolved mixtures. And in this particular example that we're going to be showing today, it's an application for biologic formulation development. And we're going to review the background on how this peak shape calibration works. First for unit or low resolution mass spectrometers, and also for high resolution mass spectrometers. And the data that we're going to talk about today is all going to be based around high resolution instrumentation. And so after our little backgrounder, we're going to dig into the meat of the topic of today's topic, which is the quantitation of the low-level degradation impurities for biologics. And we're going to quickly overview the current methods that are used utilizing mass spectrometry. And then we're going to look at a new approach that we've developed, which uses multivariate isotope modeling, which allows us to deconvolve unresolved mixtures of the various modified peptide species here, even at quite low concentrations. We're going to examine a little bit the pitfalls of the current methods and the benefits of using orthogonal methods, such as the one that we're going to be discussing today. And finally, we're going to look at the application of this mixture deconvolution application to other biologic and pharmaceutical, as well as environmental problems. And then we'll wrap it up in the end as a summary. Okay, first of all, like I said, a little background on exactly what this mass spec calibration is and how it allows us to perform accurate quantitative deconvolution or mixture deconvolution. The first thing to understand is that a typical mass spectrum that you see in your mass spectrometer software is usually reduced to what we call centroided data. And that's what the user gets presented by from the data system, as we can see from this example right here. However, the raw signal from the mass spec is not discrete lines or discrete points. It's actually a continuum consisting of lines that are fairly broad, depending upon the resolution. And this is commonly known as profile or raw scan data. And the example I'm using here is a unit resolution instrument, a simple quadrupole instrument. If you look at the centroid data, at first look, it does look like a theoretically or a true calculated mass spectrum with the intensities at given mass locations. But if you look more closely, what you really see is that the true mass spectrum contains much more than just simple centroided data. For example, under the A1 cluster here, one actually sees multiple isobars, indicating the presence of, for example, C13, nitrogen 15, sulfur 33, deuterium, oxygen 17. And this provides really key elemental composition information that is going to be lost with your typical centroiding that's done in mass spectrometry. And furthermore, if you look under the 8+2 cluster, although it's weaker, it actually contains, in this case, more detailed information regarding the elemental composition or the overall shape of the mass spectrum, especially in the presence of sulfur, as we see here. But when we do the centroiding process, all those small peaks, we're going to lose that information. And all those small peaks contribute to the overall profile or the shape of the mass spectrometer. So generally, when we're doing formula identification, we typically relegate that to high-resolution systems such as TOF or Orbitrap. But if you look at the spectrum of various formula, even at low resolution, the profile data is actually quite distinct, okay, for every formula due to these contributions of these underlying peaks. It's just that they're not fully resolved. And in actuality, there's significant detail in this ion fingerprint to provide very accurate formula identification as well as quantification. And that's going to be our topic today. So, for example, under the A+1 peak, there's all our isotopes. So how do we do this calibration? If you look at a conventional mass spectrometer calibration, the calibration that occurs in the instrument generally only corrects the position of the mass position of the peak. Doesn't do anything with the line shape. So if we actually compare the measured mass spectrum with what we would call a true mass spectrum, which is something that we can calculate based upon the isotope distribution and the known accurate masses of all the ion species, you can see that there's some significant distortions, and that's due to the electromagnetic lens that effectively is used in the mass spectrometer, which will distort that peak shapes. And it's a function of the tune, it's a function of the type of instrument. And if we could somehow correct these errors so that we could make the mass spectrometer calibrated to a known line shape, we could fit these curves very precisely. And this would give us information and that would enable us the ability to get not only what we call the isotope patterns underneath very accurately, and we term this spectral accuracy, our ability to match a true calculated mass spectrum with a measured mass spectrum is called spectral accuracy. And we can use this for identification of unknown formula as well as for deconvolution of mixture species, which is what we're going to talk about today. And so, like I said, in general, mass spec calibration only adjusts for the mass error and not for the line shape error. So how do we do this calibration? How do we correct for this instrument line shape distortion? The first thing that we do, and this is a patented approach that we've developed over the years, is we measure the we measure a known ion, an ion. We know what the formula is, and from this we're going to derive our calibration. What we first do is we examine the standard ion, and we calculate a mathematically defined line shape, okay, which is approximately the same width. So what we've done here, we've simply chosen a analytical line shape such as a Gaussian, okay, and we've matched it to the, in this case, the monoisotopic peak of a low resolution instrument. And what we're going to do is now we're going to generate the true mass spec at infinite resolution. So those are all the isotope lines at infinite resolution of a true mass spec. In other words, we can pick out the exact masses, and we know the isotope distribution. So we've calculated the mass spectrum, and we can simply convolve our chosen line shape with that to come up with a true mass spectrum, okay, which is has a known line shape, a perfect line shape. The advantage of this is that, as you can see, if we compare it to the original measured mass spectrum, it's a well-calibrated in not only the mass, but also in the profile shape itself. This is going to enable us to not only do accurate formula identification using the isotope profiles, but also to do mixture deconvolution. Once we've compared these two, this ideal mass spectrum, the true mass spectrum, with the measured mass spectrum, we can calculate a correction function or a calibration function, which is shown in green there, that when applied to the measured mass spectrum will not only correct for the mass position, or the accurate mass of the mass spectrum, but will also calibrate the line shape as well. And that's just shown here. This is how it works. Very simple. It's a convolution. We've now corrected our measured, imperfect mass spectrum to a mass spectrum that is corrected not only in mass accuracy, but also in its shape, in its known shape, spectral accuracy. And this has huge advantages, as we'll see. Okay, well, first advantage is that when we're dealing with lower resolution instruments, such as a quadrupole, you'll find the vendor usually will specify the mass accuracy to within about 0.5 to 0.2 Dalton. But since we've calibrated it to a known line shape, we can very accurately perform accurate mass calculations, even at low resolution instrumentation. For example, we can get about a factor of 100 improvement in mass accuracy using this approach for low resolution instrumentation. This just shows the calibrated mass spectrum matched, which is overlaid to what we call the true or calculated mass spectrum. And you can see how well they match. This allows us to do very accurate and highly confident formula identification. But if we have unresolved mixtures, it allows us to effectively deconvolve these unresolved mass spectra, and we can quantitatively calculate this various species. And that's basically what we're going to utilize today to look at the degradation products of these biologics. And this is, again, termed spectral accuracy. Now, it's interesting, when you go to high resolution mass spec, in the low resolution systems, what we'll typically do is we'll measure a known ion and we'll calculate the true mass spectrum from first principles, and we'll use that in our calibration. But the interesting thing is that in high resolution, you'll see that the monoisotopic peak here is well resolved from A+1, A+2, etc. So in principle, the neat thing about this is that monoisotopic peak is isotopically pure. Here we go. Oops, there we go. Let's back up here. System's a little slow. So in other words, that monoisotopic peak consists of a single line. There's no other isotopes there because it is the monoisotopic peak. So what we can do with high resolution instruments is we don't even need to have an external calibration standard. Of course, we won't, in that case, we're not going to be correcting or calibrating for the mass position. We're only going to be calibrating for the line shape or for the spectral accuracy. And so what we can do here again is we take this peak, we calculate the correction function based upon a known line shape, and we apply that to the high resolution mass spec. And what we get is we get a corrected mass spec, which you see there in blue. And we can compare that to the calculated or true mass spec, which is calculated based on first principles, and they match very well. This enables us to get extremely accurate isotope patterns. And once you know the unique isotope pattern of a particular of a particular compound, you can use that to not only do formula identification, but also to do multivariate mixture deconvolution. In other words, we could actually fit multiple species, even if they're not fully resolved, and perform mixture calculations. If you're interested in more information on this process, I suggest that you take a look at an article that was published back in 2010 in Analytical Chemistry, which goes into a great deal of detail exactly how this works. Okay, let's, now that we've got a little background, we have a little information on what is spectral accuracy and some of the advantage of it. Let's dive into our application. And we're going to talk here in our application about the quantitation of low-level degradation impurities for biologics. We're going to overview some of the current methods. We're going to look at this new approach where we can use the spectral accuracy to do multivariate isotope modeling. So in other words, we can deconvolve mixtures very accurately. And the particular problem that we're going to look at, I'm picking a particular example here for some work that we performed at BMS, looking at a digested protein, and we're going to look at one particular peptide, which turns out to be really quite interesting. And what we're looking for is the peptide deamidation. Okay, so basically aspartic acid, you have deamidation occurring, and you can actually get two species. You can get the asparagine and isospartic acid. So there's actually two species here, and that's an important point. Keep that in mind. Similarly, you can perform this kind of analysis with oligos as well. Deamination here, it's pretty similar. I'm not going to really get into this today, but really the same principle can be applied to the degradation of a lot of biologicals as well as small molecules. And the current mass spec approach to protein degradation studies is, of course, LC-MS tryptic peptide mapping, which is really considered the gold standard for looking at these degradants. And of course, the process that one goes through is you digest the protein to smaller peptides. Then you need to develop a robust chromatographic method to achieve separation between the native and modified forms of the peptides. And then what one does is it performs a relative quantitation by LC-MS peak area integration based on the accurate mass extracted ion chromatogram. So that's the typical procedure today for performing this. And we're going to take a look at this. And we're going to see some of the pitfalls in this particular method. Well, first of all, there's some challenges here. One, of course, the LC method development can be very tedious. The LC separation itself can be quite long. It can be almost up to 2 hours. It's not totally unheard of. And that means it's a low throughput, time-consuming process. The other problem with it, and this is perhaps more serious, is that how do you validate that you're actually separating the native and the modified forms? This is a challenge. The MS overlap of native and modified forms can be challenging, even for the highest resolution mass spectrometers. And we're going to look at that today. It's actually quite interesting. And there's a potential, and this is the bad part, for basically not being able to detect these modifications due to these interferences. And again, we're going to look at a particular example today. This is the separation that we performed. This particular peptide that we're going to look at looked like if we performed the XIC using about a 5 ppm window, an accurate mass XIC. These two windows are of the monoisotopic peak of the modified species and the A+1 peak of the native species are only separated by about 10 ppm. But you can see here in the XIC results, it looks like we have very good resolution of the native, which seems to elute at about 63 minutes, and the deaminated form of that particular peptide, which occurs at about 63.3 minutes. So let's validate this, okay? Are we sure that they're fully resolved? And what we did is we used our spectral accuracy mixture, our spectral accuracy calibration using these S-clips, which is the self-calibrated line shape isotope profile search, to match and validate the peak purity. If the formula composition of that particular peptide does not match the pattern, the isotope pattern, it's going to give us some error in what we call the spectral accuracy. And I think that will become clear as we look at that. So the actual formula for the this particular peptide is C80H17 and 19025. So what we do in our software is we simply type in this particular formula species, and we let it do its match, and we can compare the true mass spectrum, which is calculated, with the calibrated mass spectrum to see how well it matches. And that should give us an indication of the purity of that particular peptide. And again, I should mention that we're actually going to be doing the analysis over the native peak here at 63 to make sure it's pure. So we perform that analysis, and there's the peak at 63 that we're analyzing. And what you see here in the green line, okay, is the calculated or true mass spec based upon principles. And the black line here, which you see doesn't actually match up very well, is the calibrated mass spec. They don't match very well. The isotope pattern is poor. And in fact, we can come up with a metric for the spectral accuracy match, and it's about 91.8%. This is not a very good match, okay? Typically, really good matches start to approach about 99%. So it is an indication to us that this is not a pure peak, okay? Something's going on. And the interesting thing is, if you look at the peptide deamidation, okay, remember, there is an isomer. And the question is, do they elute at the same time? If they don't, okay, there's a possibility that there is an unresolved deaminated form that's interfering with the native peak, okay? And how do we tell this? Well, it's pretty simple with our mass spec mixture analysis. What we can simply do is we can tell the software to not only match the native form, but also apply a modification, and this is the modification that occurs to the formula in the deaminated form, and then do the spectral match. So it's really a mixture deconvolution, and the only way that this is possible is due to the fact that we've calibrated the line shape so we can get a very accurate and easy modeled line shape profile, isotope profile. And again, if you do the search, the spectral accuracy dramatically improves up to about 98.4%. That's pretty good, okay? And if you visually look at the isotope pattern, you'll see that the peaks match quite well now. There's not that error that we saw before. The other thing that's interesting here is that since we're doing the fit, we can give you the quantitative information. We can tell you how much of each species, the native and the deaminated form, are in that particular peak, and they're unresolved, okay? And it turns out about 90% of it is the native form, and about 10% is the deaminated form. However, if you look very carefully at this calibrated spectrum versus the true spectrum, the calculated spectrum, you'll still see that there's some error here in the A+4 and the A+5, and that's significant, okay? So what's going on here? What we did is the other possible known degradation pathway that is known to occur here is oxidation. And if you look at this oxidation of tryptophan to quinine, you'll see that after the oxidation, the change in the molecular weight is about 4 Daltons, okay? And if we go back here, you'll see that this is actually done at charge 2, so this is actually only half a step or half a Dalton. But you can see here at the A+4 peak, indeed, that's where the error starts to show up. So that's a good indication, okay, that maybe this is a potential interference, another degradation product. And indeed, what we can do is we can tell the software to look for another degradation variant and do the model. So it's going to model the native form, it's going to model the deaminated form, and the oxidated form to do the fit. And lo and behold, what you get is extremely good spectral accuracy. This is a near perfect match, extremely good. And again, we get the quantitative information of about 90% native, about 10% deaminated, and about a little over 1% of the oxidated form. Okay, really excellent fit. This is a really good method to validate how well. It's an orthogonal method to validate how well your method development in the accurate mass XIC peptide mapping is performing. So what went wrong with the accurate mass XIC? And if you, the things to think about is working with centroid data can be very deceptive, and we're going to look at that a little bit. And that it's important to understand that the mass spec instruments, although on the screen we see single lines that represent mass positions, the mass spec instruments actually have finite resolution, okay, as we see that when we measure the raw spectrum, for example. And that these modifications can have serious overlap of the monoisotopic peak of the native form and of the A+1 or even A+X of the modified forms, as we saw here in the oxidized one, degradant. And so these adjacent mass spec peaks, they can interfere. They can mask the chromatographically unresolved modification, even at very high mass accuracy. So this is just a graph of the native and the deaminated forms. And as you can see here, obviously the A+1 of the native form is very close, within about 9 millidaltons here of the deaminated form, and we're trying to resolve those two with an accurate mass XIC. Okay, so and then of course at all the other isotope peaks, you know, there's a potential for interference there, even at high resolution. So what one does in the accurate mass XIC method is we choose windows which we think are narrow enough to be able to differentiate these native and this deaminated form. And so when we look at the mass spec from the instrument, you know, we're thinking about it in terms of these centroid positions like that, very infinitely sharp, narrow bands. And we choose our accurate mass windows, maybe too aggressively, to be about, in this case, 4 or 5 ppm. And this, but this was measured on an Orbitrap at about a resolution of 35,000. But in reality, if you look at the actual data the mass spectrum is producing, it's actually these line shapes, which are actually much broader than, and we're only seeing the centroided data of the instrument, which is just essentially the peak picking of this profile data. So this is what your mass spec really measures, and as you can see, there's substantial overlap in these two bands at this particular resolution for these modified and native species. Okay, so let me explain what I have here. What we're doing here is I'm showing you the 2 XIC windows that were chosen. to differentiate between the modified and the native forms. And this red line here actually is the monoisotopic peak of the native form, of the modified form. And this black line here is the, I'm sorry, this is the A+1 of the native, and this is the A of the modified. So when you add these two together, which effectively is happening in your mass spectrometer, it actually shifts the centroid position that the instrument measures away from both peaks. Here we have a 50-50 mixture of the native and the modified forms, and lo and behold, the centroid that the instrument actually detects actually sits between these two windows. So you wouldn't see either form with this chosen XIC window. You'd miss it entirely. Now, in the case that we looked at where we had about 10% of the modified form, what happens is when you add these two peaks together, shown in green here, so we're adding the red, except that we're scaling it to 10%, and we're adding the black, which are scaled to 90%. The peak shifts into of the native, of both the native and the modified form, shift over into one of the XIC windows, so we only see the native form. Effectively, the modified form is hidden from us. That's a problem, okay? And that's where the error comes in. And actually, the peak separation now, if you look at the centroid, is only about 0.5 ppm. So what can we do about this? Well, one approach is, of course, we can go to higher resolution mass spec. So get narrower and narrower lines so that the XIC windows are going to fully resolve the lines. But what are the real limits? I mean, we don't have a spectrometer which has infinite resolution. In addition, when we go to higher and higher resolution, of course, there's a trade-off. There's a trade-off in there's lower sensitivity, there's slower scan rate, and of course, we need a more expensive, higher resolution instrument. The other thing that one has to be careful about is that these trap-based instruments, when you go to very high resolution, the ions are spending a lot more time in the trap, and that introduces nonlinearity, okay, of the ion positions and amplitudes due to space charge effect. This can be another complication. And of course, what we're proposing here is another approach as an orthogonal method to validate these impurity measurements is to use the spectral accuracy mixture analysis. Okay, so what happens if we go to a mass spec resolution of 100,000? We were running the example that we showed about previously, running at 35,000. So here we have the same two plots. This is but now that the band or the line width represents what one would see in the profile for 100,000 resolution. So the red is again the modified form, and the black is the native form. If we add these two together, where we scale this modified form to 10%, we get the green line here, which again shifts over into the other XIC window. So we will never see the modified form at the level of 10% if it's unresolved chromatographically, okay? Even at 100,000 resolution. So let's go to 250,000 resolution. So at 10, so you can see what's happening now is the line widths are getting even narrower, and if we add these two together again at the 10% level, we actually do get a centroid for the modified and for the native form. So actually this does work, but we do need to go to 250,000 resolution. And if you go down to 5%, it falls apart. You cannot see the modified form in this XIC window due to the distortions of adding those two peaks together, okay? So that's at 250,000 resolution, you're limited to about 5%. So in conclusion, the accurate mass XIC can lead to incorrect estimations of biologic degradation impurities, and which can obviously have potentially catastrophic effects. The spectral accuracy mixture detection that we're talking about here, the analysis that we're talking about here, it really provides a simple, orthogonal, and a much needed tool to provide confidence in the accurate mass extracted on chromatogram data. It doesn't take any additional method development. That's the beauty of it. It's not like you have to run a separate test. You can base it off the data that you have already measured. The other interesting things, although certainly you don't like to trade off chromatographic resolution and take a shortcut, it does allow it, and we have shown this, that the spectral accuracy mixture analysis, we don't have to fully resolve the chromatographic peaks. So you could actually develop a method that allows you to do faster chromatography and provide you with higher throughput. And this has been shown to work. This has even been shown to work at some test sites without any separation at all, without any chromatographic separation at all, but just looking directly at the peptide digest. Now, that's not to say that's necessarily the approach you want to take all the time. Certainly, this changes your whole method, but it is something to keep in mind, and it can allow you to, but the method does allow you to take your current method development and validate how well it's actually working. It gives you a higher level of confidence that you've actually detected or not detected your degradants. This also allows you to work with a less costly, lower resolution mass spec instruments. You can run them at lower resolution, higher signal to noise, better sensitivity. And again, we have a large body of work behind this, which has shown that the method is very robust and accurate. And quantitatively, the numbers that you get in terms of the mixture results are comparable to accurate mass XIC methods when they work. Okay. The same mixture analysis has been applied to a variety of other applications, including oligo degradants, very similar application to what we were just talking about. We've also looked at intact protein ligand binding analysis, glycans, for example, on whole proteins using specialized time-of-flight mass spectrometers that can actually do intact protein analysis. The other interesting application is the ability to quantify the hot and cold label isotope mixture analysis for small molecule drugs, doing metabolic studies. This is shown to be a very accurate method for this, which is effectively impossible to do with any other approach. Hydrogen deuterium exchange quantitation for biological environmental applications, mixture decomposition, in low resolution GC and LC instruments. That's the other interesting thing, is the bands do not have to be fully resolved in order to apply this techniques. And also, when you're using GC and an electron impact mode, we can actually do deconvolution of the multiple fragments using this approach very easily. So thanks a lot for listening to what we have to say today, and thanks for attending this webinar. Please feel free to contact me with any questions. We're going to open it up for questions right now in a second, but also feel free to contact me directly at that email address. And we're always looking to work with customers and do demonstrations of our technology and become involved in collaborations. It's something else that we also welcome. And we'll also, if you want to talk to us in person, if you're going to be in Chicago next month, we will be at PitCon. And we will also be at ASMS in Indianapolis in early June. And I also welcome you to visit our website. We have a lot of nice resources on the website. hundreds of published papers on different applications using some of these calibration approaches. And with that, if you have any questions, just please message him or chat them to the host, and he'll relay them to me, and I'll be happy to try to answer your questions. Okay, well, while you're thinking about questions, or if there's no questions, I would encourage you to, if you're interested in this approach, we'd be happy to work with you on your samples to show you how some of these methods can help you in your day-to-day workflows. All right, no questions, so I'll wrap this up. Again, there's my email address. I'd be happy to talk to you in person or chat with you via email, and help you understand and apply our methods to your particular application. And with that, I'll cut this off and say thank you to everybody for attending again.